So again, good afternoon, all of you. Welcome to this lecture of Applied Thermodynamics. So today we solve one more numerical related to single acting, single stage reciprocating air compressor. Then we'll see the actual indicator diagram, and then we'll move towards the multi-stage compression. Okay. So I hope my voice is audible, video is clear, and you are able to see the screen. Right. So write down the numerical. A single stage reciprocating air compressor delivers 0.6 kilogram per minute of air at 6 bar. The temperature and pressure at the end of suction stroke are 30 degrees Celsius and 1 bar. So at the end of suction stroke, so here is the indicator diagram. Can anybody tell me what is the end of suction stroke? Which point represents end of suction stroke? Point 1. Any other opinion? What is the end of suction stroke? Huh? Point 2. Huh? Yeah. So see again, this is the indicator diagram. Point 1 is the end of suction. Again, 1 to 2 is a compression. 2 to 3 is the delivery of pressurized air. 3 to 4 is the suction, and 4 to 1 is the again intake of outside air, and 1 at the 1 the suction stops. So at the 1 piston is at it is at BDC. At point 3 piston is at TDC. The clearance, the bore diameter is given 100 mm and stroke, that is length of stroke is 150 mm. The clearance is 3% of swept volume. So that is the ratio is given here. VC by VS, that is 3%. Assuming the index of compression expansion to be 1.3. So this index here, PV raised to N, that N here it is 1.3. So find volumetric efficiency, power required. If the mechanical efficiency is 85%, power required means shaft power required. Speed of compressor that we have to calculate. So whenever you read such problems, it is obvious that at first you have no idea how to proceed. So always start with what is possible. Okay, in this problem or any problem in life, start with whatever possible, and eventually you will find a solution for everything. So given here it is, mass flow rate is given. Okay, later you convert this into per second. Okay, so don't forget this. Pressure P2, discharge pressure is 6 bar, intake pressure or suction pressure is 1 bar, intake temperature is 30 degrees Celsius or 303 Kelvin. A bore diameter is 100 mm or 0.1 meter, length is 150 mm or 0.15 meter. Then we see clearance volume is 3% of Vs, that is 0.03 times Vs. N is given 1.3. We have to calculate volumetric efficiency and shaft power and compressor speed. Now, what is the formula for volumetric efficiency? FAD divided by swept volume. Okay, FAD divided by swept volume. Now there are two approaches. Either you can calculate volumetric efficiency by FAD divided by swept volume. In this case, if you want to calculate swept volume, you need to know the speed of compressor, which is not given. So you cannot go with that formula. Another formula you have derived in the last lecture. So we'll see that formula. So this is the formula. Okay. So there are two formulas, FAD divided by swept volume. But in order to calculate swept volume, you need to know the speed of compressor, which is not given. So we cannot use this formula, first formula. Second formula we have taken in the last lecture, the derivation for the volumetric efficiency. So here it is 1 minus K. K is the volume ratio or clearance ratio into P2 by P1 raised to 1 by N minus 1. Now in this case, clearance ratio is given, VC by VS is given, that is 0.03, 3% of VS. N is given, so K is given, N is given, P2 is 6 bar, P1 is 1 bar. Easily you can calculate the volumetric efficiency. So calculate volumetric efficiency. 0 point. Yes, those are in online mode. Calculate. So Pranali, Akanksha, Asde, Tejas Pawar, Ayush Wale, Swaranjali Deshmukh, Bodke Jadhav, Neelam Sutar, Yamgar. Huh? Why? Why? Is it not visible? Yamgar is everywhere present. Those are in online mode. Calculate efficiency, volumetric efficiency. Now, what is the problem? Why people are not able to? Chat is enabled. How much you calculate? Let us say 0.91, correct. So 91% is the volumetric efficiency. So this is the answer number 1. Now next is to calculate shaft power. The formula for the mechanical efficiency is mechanical efficiency is equal to indicated power divided by shaft power. So shaft power is the power delivered by the prime mover, motor or diesel engine to the compressor. During the transmission, various losses occur, and that's loss because of that indicated power is less than shaft power. Now, indicated power can be calculated by the formula. We have two formulas here, or one formula. So PV, you can write P1 V1, or you can write this as MRP1. So this formula is there. Now N is known 1.3, M is given 0.6 kg per minute converted into kg per second divided by 60. R for air it is 6,287. T1 is given 303. P2 by P1 is given, N is given. Calculate indicated power. Calculate indicated power. Right. Also write down. Just don't just calculate. Write down also. Dange, roll number 27. Calculate. Again, Dange, don't repeat the mistakes. Pranali Gaikwad, 9752.6. So, what is the answer? So, 1.92 kilowatt, correct? Huh? So, Pranali, please check your answer is different. Pranali Gaikwad. Others, why others are not calculating? I have a doubt that they are not in campus or they are not attending, just they have logged in and attending. Picture वाला क्या लगता है? Picture वाला क्या लगता है? हाँ, है ना? And now calculate the shaft power. So the formula is there for mechanical efficiency equal to indicated power 1.92 divided by shaft power. So from this calculate shaft power, how much? 2 point. Others check. Yes, 2.267 kilowatt. So that is the shaft power. So this is answer number 2. Yes, Akshay Pawar, good 2.258. So here the schematic is given. This is shaft power. This is a prime mover. So prime mover can be an electric motor or a diesel engine. Shaft is connected to compressor shaft. So there some losses take place. So integrated power is less than shaft power. Okay. Then the compressor is stored in the storage tank. On that there is a pressure gauge. Okay. So in the cold storage, we all have seen there was a receiver tank. On that receiver tank there was a pressure gauge, right? Okay. Now third, we have to calculate speed of the compressor. How to calculate speed of the compressor? So there is a formula of swept volume Vs. What is the formula for Vs? The volume into speed of compressor. Okay. Now once you know length is given, diameter is given. If you know Vs, then ultimately you can also calculate speed of compressor. So here we already calculated the volumetric efficiency, that is equal to fresh air delivery divided by Vs swept volume. Okay. Now here we have to calculate FAD, and by knowing FAD and volumetric efficiency, we can calculate swept volume. So FAD, fresh air delivery, is nothing but MRT1 divided by P1, right? So it is by ideal gas law, P is equal to MRT, and then M is given, R we know, T1 we know, divided by pressure, that is 1 into 10 to the power 5 Pascal. So from this, calculate fresh air delivery. So how much? 8 point minus 3. So it will be 0.08696 meter cube, right? That is the fresh air delivery. Volumetric efficiency we calculated previously 0.91. Now from this, calculate swept volume. Okay, Akanksha Jadhav, good. Now calculate Vs. So it comes out to be 0.5733. Is it correct? No, sorry. Calculate in meter cube per second. How much did you get? 9.55. 10 to the power minus 3. Okay. Now why we calculate Vs? Because we want to put here. So we'll put the values of Vs here, D and L. So put the value of Vs here. So first calculate by this value, 9.55 into 10 to the power minus 3. Put here is equal to pi by 4, 0.1 square into 0.15 into n. So by this you will get the speed in RPS. Then you can convert it into RPM. No problem. So this Vs is a meter cube per second. Put it in this equation, calculate N. So that N will be in RPS. So what is the N? तुम्ही स्टेप नाही केले तरी चालतं या स्टेजला आता कन्वर्जन इनटू मीटर क्यूब पर हे नाही केलं तरी चालेल. Directly you can take 9.55 into 10 to the power minus 3 here on LHS. Calculate n. 486. How much? 1.12 into minus 4 minus 5. What will the unit? RPS, right? Because this is in meter cube per second. So this will be RPS. Now convert this into RPM. How to convert into RPM? Multiply by 60. So multiply this by 60. You will get the value in RPM. So the RPM is 486, or is it correct or wrong? Huh? बरोबर आहे. तुम्ही काय करा 9.556 तर किती ते सांगा. 8.11 into हे आरपीएस मध्ये आहे का? किती येते? 8.11 into 60 करा, किती येते? 486.63 आलं की आरपीएम मध्ये आलं. मी काय सांगतो अजून ऐका की जी स्टेप आहे, व्हॉट आय हॅव डन हियर, आय हॅव कन्वर्टेड मीटर क्यूब पर सेकंड इनटू मीटर क्यूब मिनिट. तुम्हाला ही स्टेप करायची असते करू शकता, किंवा डायरेक्टली तुम्ही 9.55 या इक्वेशन मध्ये वापरा, तुम्हाला एन ची व्हॅल्यू मिळणार आरपीएस मध्ये. सो हे व्हॅल्यू चुकली आहे तुमची, इथे किती यायला पाहिजे? दिस कम्स आउट टू बी हाऊ मच? आदित्य, हाऊ मच? 8. This comes out to be 8.11 RPS. You multiply by 60, you will get in RPM. That is 486.63. Okay. Clear? So once again, I will repeat the numerical. What happened here actually? So you had a reciprocating air compressor. The pressure ratio होता 6. सिलेंडरचं डायमीटर आणि स्ट्रोक लेंथ दिलेली तुम्हाला. सक्शनचं ते एअरचं टेम्परेचर आहे 30 डिग्री सेल्सिअस दिले आणि प्रेशर 1 दिलेलं आहे. एअरचं तुम्हाला फ्लो रेट देखील दिलेला आहे. एवढं सगळं दिल्यानंतर त्यांनी विचारले व्हॉल्यूमेट्रिक इफिशियन्सी, शाफ्ट पॉवर अँड स्पीड ऑफ कॉम्प्रेसर. व्हॉल्यूमेट्रिक इफिशियन्सी दोन फॉर्म्युले आहेत, एफएडी डिवाइड बाय स्वेट व्हॉल्यूम आणि हा दुसरा आपण गेल्या लेक्चरला डिराइव्ह केलेला. ह्या केस मध्ये काय प्रॉब्लेम आहे, स्वेट व्हॉल्यूम काढायचं असतं की तुम्हाला आरपीएम माहित असणं गरजेचं आहे, पण यामध्ये दिलेलं नाही. सो विल यूज द सेकंड फॉर्म्युला. बाय दिस फॉर्म्युला विल गेट द एफिशियन्सी, व्हॉल्यूमेट्रिक एफिशियन्सी आहे 91%. दिस इज व्हेरी गुड एफिशियन्सी. याचा अर्थ काय की जास्तीत जास्त एअर हा कॉम्प्रेसर डिलिव्हर करतो. थेरॉटिकलच्या जवळ आहे ऍक्च्युअल. त्यानंतर दे आस्क टू कॅल्क्युलेट shaft power. So there is a formula for mechanical efficiency. It is equal to indicated power divided by shaft power. We calculated indicated power by the formula 1.92, and by this we got the shaft power as 2.286. Then last was speed of compressor. How we know speed of compressor? So there is only one equation, formula is there which involves speed of compressor, that is formula for VS, that is volume of sweat volume into RPM. So here we calculated VS from volumetric efficiency. So formula is volumetric efficiency equal to FAD, pressure delivery divided by sweat volume. Pressure and delivery formula is there, MRT1 divided by P1. From this we calculated pressure delivery, and now from this we calculated VS. As we know the VS, I put here value of VS, D and L. Finally, I will get the value of N as 486.63 RPM. Correct? म्हणजे ह्यात तुम्हाला फक्त त्यांनी प्रेशर रेशो दिलेला आणि इनलेट एअरची कंडिशन दिलेली. त्यावरून तुम्ही डायरेक्टली सांगू शकता की स्पीड ऑफ आरपीएम इज दिस. Now moving on, now we'll cover the actual indicator diagram. Okay, we'll cover the actual indicator diagram. So we all know the theoretical indicator diagram, that is 1 to 2 2 to 3 to 4. Here this is clearance volume. 0.3 is TDC, 0.1 is BDC, correct? Piston moves from BDC to TDC. 1 to 2 is a compression, isentropic compression. 2 to 3 is a discharge of compressed air. 3 to 4 piston moves from TDC downward. At point number 4, suction valve opens. Outside air is taken inside from 4 to 1. Again, 1 to 2 compression. At point number 2, discharge valve opens. Compressed air is taken out from 2 to 3. So this was the theoretical indicator diagram. Now what happens in actual compressors? Let us see. Okay. Now when piston is moving from 3 to 4, so this is a starting to suction, right? Starting to suction. Theoretically, at point number 4, the suction valve should open. 4 ला suction valve open व्हायला पाहिजे आणि air आत यायला पाहिजे at constant pressure. But तसं होत नाही. What happens? The pressure further drops. The pressure further drops to create sufficient suction, and this is drop in pressure. It is called as intake depression. Okay. At the intake stroke, this is a depression in pressure. The pressure drops to this value, and then the valve opens. Okay. Now after this also, the air is not taken inside at constant volume. The pressure continuously changes in waveform. This is because of valve bounce. So valve, suction valve is there. It kind of vibrates due to vibrating motion of valve or bouncing motion of valve. There is a wave nature in the pressure value is observed. Then at this point, air is taken inside and reaches to point number 1. So this here it is called as intake depression. Okay, understood? Now again piston moves from BDC, point number 1 to TDC, point 2. So this is a compression stroke. At point 2, again it was assumed theoretically that discharge valve should open. But that's hot nahi. Again, the pressure has to be little bit more in order to open the discharge valve. So this is a higher pressure. Actual made discharge pressure is higher than the theoretical one. Again, the discharge in theoretical it is at constant pressure, horizontal line, but in actual again due to bounce of discharge valve, the pressure shows wave behavior, and again air is behavior. So this is a difference between theoretical indicator diagram and actual indicator diagram. So draw this diagram. Show this intake depression, valve bounce. So this means this is the extra work which is consumed by compressor. This is theoretical work. This is the extra work consumed by compressor. So I'll read this. 1 to 2 to 3 to 4 to 1 theoretical PV diagram. At 4, the inlet wall does not open due to there must be a pressure difference across the wall to open inlet wall inertia. Okay, so sufficient suction pressure has to be created, and then there is a momentum inertia of the wall. Pressure drop continues till sufficient level for wall for force to its seat, for wall to force its seat. Some wall bounce is set. There is this wavy line observed. Eventually, pressure sets down at a level lower than the atmospheric pressure. So this is lower than atmospheric pressure. The negative pressure difference is known as intake depression. So this vacuum, whatever generated, this is called as intake depression. Similar situation appears at 2, that is at the start of delivery. Pressure rise followed by wall bounce, and the pressure settles at a level higher than the delivery pressure level. Air delivery to the tank receiver sensitivity of called as receiver pressure. So discharge pressure is also called as receiver pressure. Okay, so this was the actual indicator diagram. So there will be one theoretical question. Usually it is asked in the offline exam. Explain actual indicator diagram. So this is it. Now we'll move towards our today's chapter or topic. Topic that is multi-stage compression. Okay. Here it is just formula for fresh air delivery. Already we have covered. Now, before going to the multi-stage, so give the title Reciprocating Air Compressor Multi-Stage or Multi-Stage Reciprocating Air Compressor. Give the title Multi-Stage Reciprocating Air Compressor. So before going to the multi-stage, let us understand the requirement or what was the limitations of single stage. Okay, up to this point we have studied only single stage compression. म्हणजे त्यात फक्त एकच compressor होता, त्यात एकच piston होता आणि त्यात एक cylinder होता. That is what we have covered up to this point. आता let us understand the limitations. Okay, आता single stage compressor तुम्ही घेतला तर त्याचं एक प्रेशरचं लिमिटेशन आहे. ते जास्तीत जास्त 3 ते 4 बार पर्यंत तुम्हाला डिस्चार्ज प्रेशर देऊ शकतं किंवा 5 बार पर्यंत देऊ शकतं. If you go above 10 bar, तुम्हाला 10 बार पेक्षा जास्त जायचं असेल, so there is a limitation to the single stage compressor. त्यापेक्षा जास्त प्रेशर तुम्हाला देऊ शकत नाही. Again, if you try, तुम्ही म्हणला नाही हट्ट धरला नाही मला तर सिंगल स्टेजच करायचं आहे. तुमचा एक प्रेशर आहे 15 बारचं डिस्चार्ज प्रेशर तुम्हाला द्यायचं आहे. तुम्ही हट्ट धरला नाही मला सिंगल स्टेज नाही करायचं. त्या केस मध्ये काय होणार आहे? कॉम्प्रेसरचा साईज मोठा होणार. ओके, तुम्ही जर ठरवला की इफ आय वांट टू गो टू हायर प्रेशर रेशो 15 बार मला डिस्चार्ज प्रेशर पाहिजे, त्या केसमध्ये काय होणार की कॉम्प्रेसरचा साईज वाढणार. कॉम्प्रेसर साईज वाढणार म्हणजे सगळ्याच साईज वाढणार. पिस्टनचा साईज वाढणार, त्यातल्या सिलेंडरचा साईज वाढणार, त्याचा संप वाढणार, त्यातले जे पार्ट्स आहे कनेक्टिंग रॉड, क्रँकशाफ्ट, ह्या सगळ्यांचं साईज वाढत जाणार. त्याला लागणार जे फ्लायव्हील असतं, फ्लायव्हील तुमचं कव्हर झालंय का डिप्लोमामध्ये? मे बी झालं असेल. So there is another term which is called as flywheel. Flywheel it is for the mass balance. म्हणजे तुम्ही गाडीचं ऍक्सिलेटर 0 केला तरी पण त्या केसमध्ये गाडी पळत असते. तर ते कशामुळे असतं? फ्लायव्हील. फ्लायव्हील मध्ये ती एनर्जी स्टोअर झालेली असते, त्यामुळे तुमचं स्पीड नेहमी एक कॉन्स्टंट राहतो किंवा त्याचे व्हेरिएशन जास्त होत नाही. एकदम जास्त स्पीड आणि एकदम झपकन गाडी 0 येते असं होत नाही. 40 ची गाडी असेल ती हळू 10, 30, 20, 10, 0 होत येते. बिकॉज ऑफ फ्लायव्हील. फ्लायव्हील मध्ये ती एक्स्ट्रा एनर्जी स्टोअर झालेली असते. मग तसे फ्लायव्हीलचा देखील साईज वाढतो, वॉलचा साईज वाढतो, सगळ्याच गोष्टीचा साईज वाढतो. देअर क्रिएट्स अ प्रॉब्लेम ऑफ इम्बॅलन्स. म्हणजे जे मास बॅलन्स असतं आतलं त्यामध्ये इम्बॅलन्स तयार होऊ शकतो. व्हायब्रेटिंग नॉइजेस वाढू शकतात, व्हायब्रेशन्स वाढतात, नॉइज वाढतात. एक प्रकारे ती सिस्टीम अनडिझायरेबल होऊन जाते. ओके, सो देयर इज लिमिटेशन फॉर सिंगल स्टेज compressor. It requires heavy working parts. It has to accommodate high pressure ratios. There is an increased balancing problems, high torque fluctuations, and it requires heavy flywheel installation. Again, त्यामध्ये कूलिंग साठी ऑइल वापरतात. ऑइलला लागणारा पंप असतो. हे असे एक प्रकारे फारच ते सिस्टीम मोठी होऊन जाते किंवा कॉम्प्लिकेटेड होऊन जाते. सो देयर इज अ डिमांड फॉर मल्टीस्टेजिंग. आता मल्टीस्टेजिंग मध्ये काय होतं? आधीचा जो छोटा कॉम्प्रेसर होता तसंच अजून एक तुम्ही इन्स्टॉल करायचा. आधी समजा येणारा याचं प्रेशर 1 बार असेल, हा प्रेशर करणार 5 बार. 5 बारची एअर परत तुम्ही पुढच्या कॉम्प्रेसर देणार, इट विल अगेन इन्क्रीज फ्रॉम 5 बार टू 10 बार. म्हणजे 2 स्टेज मध्ये तुम्ही कॉम्प्रेशन केलं. सो that is why the name is given multistage. So why multistage compressor? High temperature rise leads to limitation for maximum achievable pressure rise. Discharge temperature shall not exceed 150 degrees Celsius and should not exceed 135 for hydrogen rich services. So there is a limitation for the temperature also. A multi-stage compressor compresses air to the required pressure in the multiple stages. Multiple stages मध्ये 2 असू शकतात, 3 असू शकतात, 4 असू शकतात, depending on the application. Intercoolers are used in between each stage to remove the heat and decrease the temperature of gas so that the gas could be compressed to higher pressure without much rise in the temperature. आता ह्यात प्रॉब्लेम असा होता की तुम्हाला प्रेशर जास्त पाहिजे, तुमचा ऑब्जेक्टिव्ह आहे की प्रेशर वाढलं पाहिजे, बट विथ प्रेशर टेम्परेचर ऑल्सो रायझेस, सो दॅट शुड नॉट बी देअर. आता तुम्ही परवाच्या विजिट मध्ये बघितलं असेल, ज्यांनी कॉम्प्रेसरचं इनलेट टच केलं त्यांना कळलं असं की ते फार थंड होतं आणि त्याचा आउटलेट तुम्ही टच केलं तर एकदम हॉट होतं. सो विथ इन्क्रीज इन प्रेशर टेम्परेचर ऑल्सो increases. And this is the schematic of the multi-stage compression. So let us understand one by one. So there are 3 cylinders here: low pressure cylinder, intermediate pressure cylinder, and high pressure cylinder. So there is air intake. आता air येते कितीला? T1 T1. Mostly it is 1 bar and 30 degrees Celsius. Now I am compressing at low pressure. So its pressure increases to P2, temperature increases to T2. Now in between these two intercooler is installed. There is a cooling water which is flowing through the intercooler. Hot air passes and there is a heat exchange. Again the temperature T2. Ideally it is reduced to T1. So outlet is, so intercooler again it operates at constant pressure. So this pressure does not change. So P2 remains P2, but T2 temperature reduces to T1. Right? Now inlet to intermediate is P2 T1. Again there is pressure rise, so P2 rises to P3, T1 rises to T3. Again there is an intercooler operates at a constant pressure, so P3 will remain constant, but temperature T3 will reduce to T1 ideally. Okay. And then there is a third stage or high pressure cylinder. So again P3 is increased to P4 and T1 increases to T4. Okay. So this is a multi-stage compression. Okay. Series of arrangement of cylinders in which the compressed air from earlier cylinder, that is discharge, becomes the intake air for the next, that is intake. LP is low pressure, intermediate pressure, and high pressure. Intercooler compressed air is cooled between the cylinders at constant pressure. So draw this diagram and show this also. This is very important. So draw this schematic. So what is multi-stage? Write down that sentence. Series arrangement of cylinders in which the compressed air from one cylinder or earlier cylinder becomes the intake air for the next cylinder. Okay, now let us understand the indicator diagram for this multi-stage compression. Huh? What's the series arrangement of cylinders? So what is multi-stage? Series arrangement of cylinders. So that word is very important, series arrangement. Okay, so there are two arrangements, series and parallel. Series arrangement of cylinders. Okay. Now let us understand the indicator diagram for the multi-stage compression. Okay. So I'll explain one by one and then you can draw. So don't draw now. So this is a indicator diagram, pressure versus volume. Now there are three cases we'll consider. First case is for the same pressure ratio, we have employed a single stage compression. म्हणजे फार असा एकदम मोठा साइजचा आपण compressor वापरला आहे. So its indicator diagram will be simply 1 to 8 to 5 to 7 to 1. Correct? So that will be the indicator diagram for single stage compression. Just 1 to 8 to 5 to 7 to 1. Okay? As simple as it is. A second case, आपण वापरलाय two stage compression but without intercooling. Without intercooling means there will be no cooling of air after first compression. So that means again it will be 1 to 2 low pressure compression, 2 to 8 high pressure compression, 8 to 5 discharge, 5 to 7 suction, 7 to 1 inlet air. Correct? This is without intercooling. Third case. So a third case is two stage compression with intercooling. So there are again two cases, perfect intercooling and imperfect cooling intercooling. Okay. What it means? So this is a low pressure. So this is again schematic of multi-stage is given. Low pressure compressor, high pressure compressor. In between them they have a intercooler. आता initially P1 T1 temperature होता, conditions होता. After pressurization P1 becomes P2, T1 becomes T2. आता इथे intercooler मधून pass केलं. Now function of intercooler is to cool down the air. आता perfect intercooling मध्ये काय होतं? So whatever temperature is at the outlet of intercooler, it is same as the inlet air. So that means here T3 becomes T1 or T3 is equal to T1. So that is the perfect intercooling. जे एअरचं टेम्परेचर आहे इंटरकूलरच्या बाहेर येताना ते सेम त्याच्या इनलेट सारखंच पाहिजे. देन इट बिकम्स अगेन P2 to P3, T3 to T4. इनपरफेक्ट इंटरकूलिंग म्हणजे जे टेम्परेचर आहे एअरचं इंटरकूलरच्या बाहेर इट इज स्लाइटली ग्रेटर दॅन द इनलेट टेम्परेचर. That is imperfect intercooling. Now let us understand on the indicator diagram. So 1 to 2 is here low stage compression. 2 to 3 is the intercooling. 2 to 3 is the intercooling. Again 3 to 4 is high pressure compression and 4 to 5 is the delivery. Okay. So here are 1 to 2 that means low pressure compression. 2 to 3 here it is the intercooling and 3 to 4 is the high pressure compression. So this is a multi-stage compression. Now compare all three cases. Okay, so for time being ignore this dotted line and these three. Now compare all the three cases. पहिल्या केस मध्ये work required किती होता? पहिल्या केस मध्ये work required was 1 to 8 to 5 to 7 to 1. Correct? Second case मध्ये work required किती होता? Again 1 to 2, 2 to 8, 8 to 5 to 7 to 1. Third case मध्ये work required किती होता? 1 to 2, 2 to 3, 3 to 4, 4 to 5, 7 to 1. So with the help of intercooling, we are able to minimize or to reduce the compressor work of this magnitude. म्हणजे हा जो hatch area तुम्हाला दिसतोय 2 to 8 to 4 to 3. So this is a reduction in compressor work. So that is the beauty of intercooling. With the help of intercooling, we are able to reduce the compressor work. Understood? हा पॉइंट फार महत्वाचा आहे. So this will be asked in MCQ or this is a conceptual. Very much. Actually, it is the beauty of intercooler. Not only it reduces temperature, but it also reduces compressor work. Temperature reducer होतेच, त्यात काय वाद नाही. But with that reduction in temperature, the compressor work also reduces. Okay. Now then comes the next question: perfect intercooling and imperfect intercooling. If it is imperfect cooling, that means T3 is greater than T1. Then the point number 3 lies somewhere here. So there is a constant temperature line. Actually, it is there. I will draw. Okay, from 1, if I want to draw a constant temperature line. So for perfect intercooling, that for constant temperature line will pass through point number 3. So this is a constant temperature line from 3 again to 4. If it is an imperfect intercooling, then in that case, point 3 will lie somewhere inside here. Okay. So draw this diagram and don't draw this 3 and all this. Okay. So this is not required. Just draw this 1 to 2 and don't draw this hatch lines or this dotted line. Okay. So need of intercooling, draw this indicator diagram and first write down case number 1, single stage compression. Single stage compression. Now in single stage compression, what will the compressor work? Compressor work will be equal to area. How much? 1 to 8 to 5 to 7 to 1. So write down with the need of intercooling case 1. Okay. Or you have drawn this diagram. First draw this diagram, then we can write down the text. Draw this indicator diagram. So don't draw this 3 dash, this dotted line, this hatch part. So don't draw this. Just draw remaining part. This whole diagram, then 2 to 3 to 4. Then between this hatch portion, this much you show. So here we are dealing with two pressures. That is a low pressure and high pressure. So here inlet pressure is P1, intermediate pressure is P2, that is after first compression, and final discharge pressure is P4. Okay. So under this completed, under this write down case 1, single stage compression. Okay. In single stage compression, indicated work or work required to drive the compressor will be equal to area 1 to 8 to 5 to 7 to 1. Then case 2, two-stage compression without intercooling. Okay. Two-stage compression without intercooling. Here, what will the work done? Here, work done will be equal to. So first low pressure. The low pressure मतलब area क्या है? 1 to let us say 2 to 6 to 7 to 1. This plus area to 8 to 5 to 6 to 2. Correct? High area plus high area. High area same होता है. Okay. And now give the title case 3, two-stage compression with intercooling. Two-stage compression with intercooling. In that show there are again two cases. Case 3.1 that is perfect intercooling, and case 3.2 that means imperfect intercooling. So in under this perfect intercooling, write down T3 is equal to T1. T3 is equal to T1, and in perfect intercooling, T3 is greater than T1. T3 is greater than T1. So below this, draw this schematic of multi-stage compression. This schematic: low pressure, intercooler, high pressure. Now here, what will the work required? Work required will be equal to area one to 2 to 6 to 7 to 1 plus area 3 to 4 to 5 to 6 to 3. Is it correct? Check the area in perfect intercooling 1 to 2 to 6, 7 to 1. So this below area plus 3 to 4 to 5 to 6 to 3. This area. This will be perfect intercooling. Work required in the perfect intercooling. Now with this we can say with perfect intercooling or intercooling there is a reduction in indicated power. So there is this reduction in indicated power. So write down one sentence. With intercooling, we are able to reduce the temperature of compressed air with intercooling. We are able to reduce the temperature of compressed air as well as the total indicated power required. The total indicated power required or total compressor work required. So let us write out the formulas. So for case 1, so give the title indicated power. So in case 1, what is the formula? Formula this already we have derived. N upon N minus 1 P1 V1 into bracket discharge pressure divided by suction pressure raised to N minus 1 upon N minus 1. Okay. So this formula already we have derived in previous classes. So previously we were using P2 by P1 because previously P2 was the discharge pressure. Now in this case P4 is the discharge pressure. So that is the difference. This is the work required in single stage compression. Now if I go with 2 stage without intercooler, so this will be equal to compressor work will be equal to compressor work at low pressure plus compressor work at high pressure. Compressor work at low pressure plus compressor work at high pressure. So low pressure is the area 1 to 2, 2 to 6, 6 to 7 to 1. So this will be equal to N upon N minus 1 into P1 V1 into bracket P2 by P1 raised to N minus 1 upon N minus 1. Right? So previously we have derived this equation for the compressor. So this is low stage compression. First, this formula is low stage compression work plus N upon N minus 1 P2 V2 into bracket P4 by P2 raised to N minus 1 upon N minus 1. So this is a high pressure compressor work required. And third case is 2-stage compression with intercooler. 2-stage compression with intercooler. In that perfect intercooling, in that first write down imperfect intercooling. 2-stage compression with intercooler. In that sub case 3.1 or write down imperfect intercooling. So write down this for imperfect intercooling formula will be this one. Work in low pressure plus work in high pressure. Work in low pressure is same as previous. N upon N minus 1 P1 V1 P2 by P1 raised to N minus 1 upon N minus 1. But here this high pressure work will be slightly different from the previous one. Here it will be N upon N minus 1 P2 V3 into bracket P4 by P2 raised to N minus 1 upon N minus 1. So this is the work required for the compressors with intercooler without imperfect intercooler. And next case 3.2 is perfect intercooling. 3.2 is perfect intercooling. Perfect intercooling means T3 will be equal to T1. T3 is the temperature of air after intercooling and T1 is the suction air temperature. So T3 is equal to T1. So write down this perfect intercooling. Under that write down T3 is equal to T1. So as this is an isothermal process, so T3 is nothing but T3 V3, T1 is nothing but T1 V1. So under this, write down P3 V3 is equal to P1 V1. Now also P2 is equal to P3, right? Intercooler pressure is constant, so P2 is equal to P3. So you can check the indicator diagram also. Here you can check pressure at point 2 is equal to pressure at point 3. So pressure is equal, P2 is equal to P3. So write down P2 is equal to P3. So see here, what I will do in this equation, I will replace P2 by P3. See carefully. P2 I will replace by P3 because they are equal. So it becomes P3 V3, correct? Now here we have said P3 V3 is equal to P1 V1. So whole this P2 V3 will be replaced by P1 V1. So here comes the equation n upon n minus 1 P1 V1. This is as it is from this equation, plus P1 V1. So initially it was P2 V3. Now it becomes P1 V1. In bracket P4 by P2. This represents the same. So this is the equation for perfect intercooling. In this they have taken n upon n minus 1 as common. And again we will take P1 V1 common, and finally the equation becomes n upon n minus 1 P1 V1 into bracket P2 by P1 raised to n minus 1 upon n plus P4 by P2 into raised to n minus 1 upon n minus 2. So this minus 1 becomes minus 2. Minus 1 becomes minus 2. Correct? So in books, you will find here we have written P4 by P2 because in our diagram 4 point was here. Okay. In books, you will observe here P3 by P2. So don't get scared. So in books, the P3 point is here. So as a diagram or notation changes, the ratio changes. But I found this is more convenient to understand because it goes like 1 to 2, 3, 3 to 4. So it becomes convenient. We cannot go like 1 to 2, 2 to 4 to 3. Ulta apan jau शकत. So it was more convenient. So that is why I have taken this way. Okay. And last power required to drive a two-stage compressor. What is the power required? What is the work into N divided by 60 in watts. So here N, again N will be equal to N for single acting cylinder. That is the RPM. Okay, N is RPM, speed of compressor. And N becomes, or say this, NW becomes 2N, 2 times RPM if it is double acting cylinder. सिंगल ऍक्टिंग सिलेंडर म्हणजे काय, तर पिस्टनच्या एका बाजूलाच काम होत असते किंवा एका बाजूलाच कॉम्प्रेशन होत असते. पिस्टनच्या तर दोन्ही साइडला कॉम्प्रेशन होत असेल तर त्या केसमध्ये इट इज अ डबल ऍक्टिंग सिलेंडर. So power required to drive a two-stage compressor, WC, that is compressor work into NW divided by 60 watts. Now, the last point of today's lecture I will take and then I will stop. So, the last point is related to finding out minimum work criteria. Finding out minimum work criteria. म्हणजे टेम्परेचर किंवा प्रेशर कंडिशन्स कशा पाहिजे, त्यांच्यातलं रिलेशन कसं पाहिजे जेणेकरून आपल्याला कमीत कमी कॉम्प्रेसर वर्क लागू शकतो. Before going to that, let us understand the concept of maxima and minima. So for diploma people, I don't know if this point is covered in diploma or maths. Their maths is also weak. So that is why we will first see what is maxima, minima. So let us understand there is a function called y, and its equation is like common ax cube plus bx square plus cx plus d. ठीक आहे, त्याचं एक फंक्शन आहे. एक एक्झाम्पल म्हणून घेतलं आहे, हे असं असं काय पण असू शकतं. त्याचं मी समजा ग्राफ प्लॉट केला, so it becomes like this, like it will be go up and then down, then up, down and up. Okay, so this is a graph for this function. Now there is a term called global maxima. म्हणजे ह्याची जी रेंज आहे, टोटल रेंज घेतली मोठी होईल, त्यातलं ग्लोबल जी मॅक्सिमम व्हॅल्यू आहे, दॅट इज कॉल्ड एज ग्लोबल मॅक्सिमा. सो एज यू कॅन सी हियर, पॉइंट ए is the global maxima. Then another term is global minima. So whatever lowest term is there. So in graph it is actually D, but I have taken B. So lowest point will be global minima. Then if you take a range, तुम्ही एवढीच रेंज घेतली, ठीक आहे, एवढी छोटीशी रेंज घेतली, त्यामध्ये जर तुम्ही बघितलं, so that is त्यामध्ये जर तुम्हाला सांगितलं ह्यातला कुठला मॅक्सिमम पॉइंट कोणता आहे एवढ्याच रेंज मध्ये बी टू डी मध्ये, सो यू कॅन से सी इज द मॅक्सिमम पॉइंट. सो सी स्टँड फॉर लोकल मॅक्सिमा, आणि बी टू डी मध्ये जर तुम्ही बघितलं तर इथं मध्ये म्हणू शकते डी इज द लोकल मिनिमा. सो एकतर असतं ग्लोबल मिनिमा, ग्लोबल मॅक्सिमा, किंवा लोकल मिनिमा अँड लोकल मॅक्सिमा, हे दोन पॉइंट असतात. इथपर्यंत समजलं? आता तुम्हाला काढायचं की कुठे येतं हे मॅक्सिमम पॉइंट, कुठे येतो मिनिमम पॉइंट, कुठे येतो हे काढायचं असेल तर काय करावं लागतं, यू हॅव टू टेक फर्स्ट डेरिव्हेटिव्ह ऑफ दॅट फंक्शन अँड इक्वल इट टू 0. आता इक्वल इट टू 0 काय करायचं, डेरिव्हेटिव्हचा अर्थ काय असतो, व्हॉट इज डेरिव्हेटिव्ह? डेरिव्हेटिव्ह म्हणजे आपण एक लाईन पॅरलल किंवा सॉरी टँजंट काढतो, नॉर्मल काढतो, आणि त्याचा स्लोप, द स्लोप इज गिवन बाय dy बाय dx. म्हणजे आपल्याला dy बाय dx चा स्लोप ऑफ द लाईन मिळतो, अँड दॅट शुड बी 0. हा काय कन्सेप्ट आहे, तर मी समजा इथे एक लाईन काढली, इफ आय ड्रॉ अ लाईन टँजंट ऍट दिस पॉइंट, यू कॅन सी इट इज अ हॉरिझॉन्टल बिकॉज इट इज अ मॅक्सिमा. ती जर मी मध्ये कुठे काढली असती तर त्याचा एक स्लोप आला असता. ओके, सो आय टेक हेल्प ऑफ अनोटेशन. आता ए ला काढली म्हणून हॉरिझॉन्टल, ती जर मी इथे काढली असती तर डेफिनेटली काहीतरी स्लोपची व्हॅल्यू आली असती, बट इट इज नॉट मॅक्सिमा और मिनिमा. सो whenever slope is 0, that means the line is horizontal, the tangential line at that point is horizontal, either it is maxima or is it is minima. मग ह्यातनं तुम्हाला इक्वल केल्यानंतर x ची एक व्हॅल्यू मिळते, ही x ची व्हॅल्यू परत तुम्ही डबल डेरिव्हेटिव्ह काढायचं, डबल डेरिव्हेटिव्ह काढल्यानंतर त्यात तुम्ही x ची व्हॅल्यू पुट करायची. ह्याच्यानंतर जर ह्याची व्हॅल्यू डबल डेरिव्हेटिव्हची व्हॅल्यू जर 0 पेक्षा कमी आली, सो देन दॅट पॉइंट, हा जो पॉइंट आहे x तुम्ही घेतलेला, दॅट इज अ मॅक्सिमा. जर डबल डेरिव्हेटिव्ह मध्ये x ची व्हॅल्यू तुम्ही टाकली, ती जर 0 पेक्षा जास्त आली, सो दॅट पॉइंट स्टँड फॉर मिनिमम. ओके, सो दिस इज अ जनरल प्रोसिजर फाइंडिंग आउट मॅक्सिमा अँड मिनिमम. आता हे काय करायचं आपल्याला, बिकॉज वी वॉन्ट टू फाइंड आउट मिनिमम वर्क रिक्वायर्ड, म्हणजे आपल्याला मिनिमा काढायचा. सो द प्रोसेस विल सी. So for minimum work, okay, condition for minimum work, for minimum work we have to first take the derivative. Okay, then we have to equate this derivative equal to 0. So this is the first step. They have taken the derivative, then equal to 0, and eventually we'll get a maxima, either maxima or minima. So by this equation, if you solve step by step, we'll come to this relation between the pressures. Okay, इथं P3 आहे, आपण त्या जागी P4 घेतला, राईट, एवढाच फरक आहे. सो द रिलेशन इज लाईक द इंटरमिजिएट प्रेशर इज इक्वल टू स्क्वेअर रूट ऑफ प्रोडक्ट्स ऑफ सक्शन प्रेशर अँड डिलिव्हरी प्रेशर. ओके, सो राईट डाउन कंडिशन फॉर मिनिमम वर्क. Condition for minimum work, condition for minimum work. So write down here the formula condition for minimum work. Under that, write down dW by dP. dW, this term, dW by dP2 should be equal to 0. Condition for minimum work, dW by dP2 should be equal to 0. And then after that, write down this P2 should be equal to square root P1 P4. आपल्या केस मध्ये P1 P4. P2 should be equal to square root P1 into P4, or you can write P2 square should be equal to P1 into P4. So it is a condition for minimum work. जर तुमचं सक्शन प्रेशर इंटू डिस्चार्ज प्रेशर, ठीक आहे, याचा तुम्ही स्क्वेअर रूट काढला, तो जर तुमचा इंटरमिजिएट प्रेशर एवढा असेल, so that we can say the compressor, the unit compressor unit will require minimum work. Okay. So condition for minimum work is P2 should be equal to under square root P1 into P4. Then we'll say the formulas for two-stage minimum work. So write down minimum work in two-stage RAC. RAC means reciprocating air compressor. Minimum work in two-stage RAC. Minimum work in two-stage RAC. So this question is asked for GATE examination. So we'll take in the next lecture. Minimum work required for two-stage RAC is equal to 2n divided by n minus 1 into P1 V1 into in bracket P4 divided by P1 raised to n minus 1 upon 2n minus 1. Write down minimum work in two-stage RAC is equal to 2n divided by n minus 1, this equation. P4 raised to P4 by P1 raised to n minus 1 upon 2n minus 1. And next write down minimum work required in three-stage RAC. Minimum work required in three-stage RAC. Write down this formula: 3n divided by n minus 1 P1 V1 into P4 by P1 raised to n minus 1 upon 3n minus 1. म्हणजे मिनिमम वर्क पाहिजे असेल तर तुम्हाला काय पाहिजे, पहिल्या तरीचं पाहिजे परफेक्ट इंटरकूलिंग पाहिजे, ठीक आहे. दुसरी कंडिशन काय आहे की P2 should be equal to under square root P1 into P4. That way you will get the minimum work. So with this we'll stop here. In next lecture we'll take numerical part and the comparison between various compressors, how to select the compressor. तुम्ही जर मार्केट मध्ये गेला कॉम्प्रेसरचं तुम्ही ब्राउझर घेतलं तर तुम्हाला कसं वाचायचं काय वाचायचं ते that will see in the next lecture. Okay. So next lecture will take some numericals and okay. So any doubt? So we'll cover. I'll take the recap also. Don't worry. So in today's lecture, we started with the numerical of a single acting RAC, single stage RAC, and we calculated automatic efficiency, shaft power, and speed of compressor. Then we took the next numerical. Then we saw the actual PV diagram. So in actual, the more work is required for the compression. Then we saw the need of compression, limitations of single stage compression. Then we saw the schematic of multi-stage compression. Then we saw the work required in each case, and we saw that with intercooling, not only temperature decreases, but work required also decreases. So always remember, with intercooling, less work is required. Then we saw the formulas. Lastly, we covered the maxima and minima concept, and then we saw how to calculate minimum work. So take the derivative equal to 0. आता ह्यात गॅरंटी नाही आहे बरं का, त्यांनी केलंय हे, पण ह्यात गॅरंटी नाहीये. हे जे आहे इक्वल टू 0, यातून तुम्हाला एकतर मॅक्सिमा पण मिळू शकतो किंवा मिनिमा पण मिळू शकतो. तो मॅक्सिमा आहे का मिनिमा हा कसा काढायचा, तर डबल डेरिव्हेटिव्ह काढून x ची व्हॅल्यू टाकायची. ती जर 0 पेक्षा कमी आली सो इट इज अ मॅक्सिमा, 0 पेक्षा जास्त आली तर इट इज अ मिनिमा. सो रिमेंबर दिस. Then we saw the condition for minimum work P2 is equal to under square root P1 into P4. For so minimum work required 2 stage, this is the formula. Minimum work required in 3 stage compression, this is a formula. Next lecture will take numerical. Okay. So put your attendance in the chat box, then we can stop. Offline. एक मिनट, तारीख किती 15. हाँ 4/13. हाँ 28. 34 नाही का? So with this, we'll stop here. Thank you for attending. The next lecture we take numericals related to multi-stage compression.